Welcome back, everyone. I'd like to introduce Bin Dong, who is a research scientist at Lawrence Berkeley Lab and is going to talk to us about FasTensor, a pain-free HDF5 data analysis tool that he's been working
on. Okay, thanks, Quincy. Thanks for introduction and thanks for this opportunity to introduce my work. My name is Bin Dong. I'm a research scientist at the Lawrence Berkeley Lab. Today I will share you on some work named FasTensor to enable pain-free HDF5 data analysis at large scale. This also get help from the John Wu and Suren and Hojun and from LBO and Weijia and Flori from the UC side. Let's start with some background of the motivation we developed this library. So as all we know that scientific equipment can easily generate mountains of scientific data. For example, the net source at the Berkeley Lab can produce 118 petabyte data per year, and genomic science can have 10 petabyte data per year, and high energy physics, they may generate over 200 petabytes per year. Climate science, they usually produce more data, they may go beyond 100 exabyte per year. So luckily, all this data can be represented as multi-array, and based on experience, we see that most of this data are stored in file format like HDF5, PNSSU, and others. So since the size of this data are very large, so how to find the inside of this data set is become very challenging. So it's impossible to do that manually by hand. Possible way is that to develop some data analysis program, use computer to help to do that. But developing the data analysis program has some challenge. So first you need to consider how to perform the data management task. So you need to know where your data stored and how stored, how can effectively get the data out of your storage device. So you need to also consider not of software stack that on top of your data. Even you can get your data, you are facing probably a HPC system. This system comes with thousands of computing nodes or even over millions of CPU cores. You need to know how, you need to figure out how to distribute this data on this compute node to use their computer power. On the other side, even for the same data, different people have different analysis operation on this data. So put all this together, you may face an infinite number of data analysis operations. So that makes the developing data analysis a very, very difficult task. But don't worry. So not all smarter computer science or engineering has figured out some way to help you. One of the most successful work in recent year is called data program model, especially for large data, they call parallel data program model. So in this way, they provide a programming abstraction to help you to cover all the complexity of hardware and software. And also they try to make this abstraction more generic to many data analysis tasks. You may have heard that the MapReduce that started earlier of this century is one of the most successful parallel data program model. So the original from MapReduce of Google, they have the implementation in Hadoop and Spark. So in this MapReduce program model, they only need you to master two generic data analysis operator. They call map and reduce. You only need to format your data in the abstract data type they call key-value pair, key-value tuples. So use this two generic operator and one abstract data type, you can use to express different data analysis tasks search. So there are user-defined functions like search task, value range, and other tasks. So after you have this analysis task expressed with MapReduce and the key-value tuple, you can run your analysis program on any theoretically you can run your analysis program in any hardware or software from your desktop or HPC system. But MapReduce has its own limitation in tensor data analysis. As all we know, everyone nowadays are talking about deep neural network, convolutional neural network, and Let's take this convolution as an example to explain what is limitation of the MapReduce. So since that you have two-dimensional tensor, and you want to apply a 2x2 convolution kernel on your data, and in order to use MapReduce to perform this convolution computing, you need to first convert your array into key-value pair, as I mentioned before. So in this conversion, you need to deal with lots of data transform. That actually is very expensive. So in order to perform that particular convolution operator, you need to use the reduce stage. In order to do that reduce stage, you need to duplicate lot of data from a convolution kernel nearby each other. So this duplication actually make the over data reduce very expensive. So if you are familiar with this MapReduce, you also know that they have a shuffle stage in the middle. This shuffle maybe have communication across nodes. That's also makes this worse. So we provide detail of this detail analysis for this limitation in our paper at ISC 2019. And if you are interested, go ahead to read it. So to summarize that, MapReduce is not good fit for tensor type data analysis. Remember that, let me remind you that HDF5 is actually array-based data model. So that means MapReduce is not good fit for the HDF5 based data analysis. To address this issue, we propose a new program model that's named the FasTensor. We used to call it ArrayDiff in our research paper. So the general idea of the FasTensor comes from the one definition of the tensor that says that a tensor can be defined as a multi-dimensional array and the proper transformation rules. So based on this general idea, the FasTensor has three major components. One is the array-native data program model we call SNOPE. Another major component is tensor-based abstract data type, and as well as a single transform operator. So I will introduce more detail about this in later slides. So one thing I want to let you know first that FasTensor is very friendly to HPC. It's native support NPI and directly work on certificate data format like HDF5. So it also automatically deal with chunking, go-through management, and other tough data management tasks on the parallel computing. Okay, let's introduce more detail about the stencil. That's one of the major data abstract in the FasTensor. So stencil here is the stencil here is an abstract data structure. It's used to represent neighborhood of an array. So by definition, it's as a base cell. It has any number of neighbor cells. So depends on user's requirement. The user can put any neighbor cell into that stencil abstract. So that's give a way to user to express different geometric shape or size of data for on top of the array. So this also gives our flexibility that we can split large array into some small unit. This unit can be processed automatically or out of core or parallel. So it gives actually flexibility for user to also in FasTensor, especially in the FasTensor, it gives the stencil gives the capability for user to define the operation on top of any geometric shapes. So as you can see on the figure of this slide, that you can use this stencil to express any geometric shapes. So let's touch a little bit about the SNOPE program model. SNOPE actually is short for structured locality aware program model. So since we based on the array data model, we try to capture all the locality operation on the array. So here I put MapReduce as a comparison of this SNOPE program model. So in SNOPE, you have a multi-dimensional array as your basic data structure, but in MapReduce, you have 1D list. Particularly is 1D key-value list. SNOPE uses stencil as an abstract data type to express operation. In MapReduce, you have key-value pair as a a logical data type for a user to describe operation. So in MapReduce, you have map and reduce two operator. So in slope, you only have one operator named transform. So the formula in the bottom of this slide actually show how this slope program model. So you have excuse me. You have stencil 1 that from the array A. You have stencil 2 that from array B. So transform actually can convert the data from stencil 1 to stencil 2. Use the rule that we use user-defined function to carry to the user-defined function actually carry the rule of the transform. So user run this transform actually apply the rule on the data in S1 to generate the data in S2. So that's some theory and background of the FasTensor. Let me give you some real example. So this example is just a purely C++ code. So that is the language our FasTensor library use. So as all we know that the C++ code starts from the main function, right? That's the top of this figure. So that's the start point. After inside the main function, you can use in memory a pointer A that is has type of the array that defined in FasTensor to point to a HDF5 data set that store that actually have some have a two-dimension that actually is a two-dimension data with 16 by 16 size. And let's assume that your data is your data come from 16 sensor, and each row of that data is time series data. So in some way, you want to apply a 3-point moving average on this data. So you can use this in memory point of variable A to point to that data directly, and then you can declare in memory variable B to some store the output data. So then you can call that transform function on A to generate convert the data from A to the B. So the question now is how can we describe this 3-point moving average operation? So this is, as I said before, this is FasTensor use a function called user-defined function to do this job. So here you can see that A transform UDF, B on this line they take a user-defined function. So that name is UDF-MA. So this UDF-MA is user-defined function that carry all the rule of that transform. In this particular case, that rule is a 3-point moving average. So the formula of this moving average actually show on the right bottom of this slide. So you can actually convert this formula into some C++ expression in this user-defined function. So note that this user-defined function can take stencil as input and output. User can use this relative set apply on this input stencil to get the neighbors of 1 point at before and after to express their operation. So once you put this together, you can combine this code as normal C++ code. So after you run, actually the transform function will run this user-defined function. So inside, so you can run this program either sequentially or in parallel. So basically, you run your data once, you can run. Theoretically, you can run anywhere. So this is a real example. So how the FasTensor works in the program language. So here I want to share you some of the application of FasTensor in real scientific application. So one of the project that I personally like most is the FasTensor use case in the earth science. It's from one application we call DAS. So this application has the this application is used dark fiber to monitor the environment, and then you use the data analysis pipeline to extract meaningful knowledge like earthquake wave from this noise data. So you can find more detail about this DAS application in the to reference paper and this on the slide. So they originally have a MATLAB pipeline built to do this job, but it takes many weeks. There's one time, one student from Georgia Tech convert this MATLAB pipeline to Python, because Python become popular now, but it still take an hour to perform this job. So there is one time this Georgia Tech student listen one talk about this FasTensor. They want to give that a try, and we help him and have some basic implementation in FasTensor. They found, oh, surprisingly, it only takes 20 seconds. So this also have some help from the students to do this work. Another example I like most, I want to share you today is the FasTensor use case from the plasma physics. This is some work with autonomous. So they have these people have a VPIC simulation code, and in this simulation they generate lots of data, and this data different type and they have different size. So for example, in summary, they have particle data, grid data, and field data. They have different data analysis on different data, and sometimes they want to merge different data as together as input of analysis. So they don't have the established data analysis pipeline. So mostly they just go to write their own data analysis code. So that means each time they need to suffer all the challenge I mentioned in the previous slides. So there's some chance that they learn the FasTensor, and we help them just use FasTensor program model to express all their data analysis. That makes them really happy. So this slide on the right just excuse me. This slide on some content on the right that shows some performance improvement that we consider some particle locality to make it even faster. Okay, that's some application. I will briefly go through some performance number compared with some other PR system here. So here I just take a 2-layer convolution neural network as a workload, and I only focus on fast forward step. That's one of the most expensive one. I run this analysis on very large 2-dimensional array. I compare the FasTensor with TensorFlow and Spark and the C++ implementation. C++ implementation just say, okay, I write my own C++ code. I try all my best tuning that code. Also, you know that FasTensor have convolution implementation. That's also a kind of like a public available hand tuning code. So I run this 2-layer convolution neural network on a single node or multi-cores. So I found that either case, the FasTensor are much faster than the Spark. They have beatable performance on the C++ implementation, but surprisingly, we found that these FasTensor are still much faster than the FasTensor in this test case. So we try to, as I say, we want to large scale data analysis. So based on our own experience, we have scaled the FasTensor over to 16,000 CPU cores. So in all this scale tests, we found a kind of perfect scalability. Okay, that's the major content of this talk. I want to give a summary on my talk. So we will release, we already have the release of FasTensor as a beta bucket under the management of Berkeley Lab. So we are also looking for some use case to provide educate and make Fast even better. So if you have some use case or you have some hand, just drop us a message. We have some particular request for HDF5 feature. We really want a parallel virtual data set, because when they deal with that dark fiber data, as I mentioned in the application section, so they have lots of small data. They want to merge some of them to data analysis, and their number of their small data is quite large. Okay, we want to thank our sponsor from DOE and Oscar office. We also get a lot of help from NERSC to set up our system. And okay, that's all.
Thank you, Ben.